The first example is giving us a polynomial, f of x, and is giving us a closed interval, the interval from -1 to 1. Question number 1 is asking us to verify that the function satisfies the conditions of the mean value theorem. And this again goes in accordance with what we said in class, that if we want to be able to enjoy the result of a theorem, we have to make sure that the conditions in the hypothesis of the theorem are satisfied. So in order to use the mean value theorem, we have to make sure that the function is differentiable in an open interval AB and is continuous in the closed interval AB. So here again, the closed interval is -1 to 1. And because f of x is a polynomial, I know that a polynomial is continuous and differentiable everywhere. So I say that indeed f is a polynomial. And as soon as I make that comment, then I know that it is going to be continuous in the closed interval -1, 1, and it's going to be differentiable in the open interval from -1, 1. Now that I have that nicely satisfied, then I can go to the second part of the question. Find the number or numbers that are guaranteed by the mean value theorem. The theorem says that if the conditions are satisfied, there exists a number c in the open interval from -1, 1 such that f prime of c is equal to f of 1 minus f of -1 divided by 1 minus -1. So that's a guarantee of the theorem. It's telling us that c exists, at least one c is going to exist. What I will do right now is go ahead and compute the slope of the secant line. Using this expression right here, all that I have to do is compute f of 1, f of -1, and plug everything in the formula. So for example, this is going to be equal to, using the function, 1 minus 3 plus 5 minus -1 plus 3 plus 5. All of that will be divided by 2. 1 minus -1 is going to give us 2. So whenever we simplify this, we end up getting -4 divided by 2, which is equal to -2. In other words, this number right here is the slope of the secant line that passes through the points where x is -1 and x is +1. All right. Now, continuing with the problem. Now I have to calculate the derivative at c. In other words, I know that f prime of x is going to be equal to 3x squared minus 3. So then that means that f prime of c is going to be equal to 3c squared minus 3. I know that f prime of c, if you remember, f prime of c has to be equal to -2. That means that 3c squared minus 3 equals to -2. And when I solve for c, we end up getting that c is going to be equal to plus or minus 1 divided by the square root of 3. This is approximately plus or minus -0.6. So then that means that I can go here to my graph, and at this particular value, -0.6, and here 0.6, these are exactly 2 points on the graph where the tangent line is going to be parallel to the secant line. If you notice right here, I've drawn the 2 tangent lines that are parallel to the secant line. The secant line is the red one, and the green tangent line is parallel to the red line, and so is the yellow line. The mean value theorem always guarantees the existence of at least one c where a tangent line is parallel to the secant line. But some functions are going to have more than one such c. In this case, in this function, in example 1, we were able to find two c's with two tangent lines parallel to this red secant line. Question number 2 is asking us to use the mean value theorem to show that a car that has traveled 110 miles in 2 hours must have had a speed of 55 miles per hour at least once during that 2 hours. In order to begin the problem, I let f of t be the position function of the car. Specifically, f gives the distance that the car has traveled after t hours. So after t hours, plug in the value of t in the function, and you're going to get that distance. For this problem to make sense, I will assume here that f is a continuous function. So I'm going to here say continuity is going to hold. The interval that I'm going to be working with is going to be the interval from 0 to 2. And for the sake of simplicity, f of 0 will correspond to 0 miles. And then f of 2 is going to correspond with 110 miles. Okay. This doesn't have to be the case, but if I work with the interval from 0 to 2, that makes things a lot simpler. Now I'm going to go ahead and calculate the average speed, like the slope of the secant line. Here I'm going to have f of 2 minus f of 0 divided by 2 minus 0. This is going to be equal to 110 divided by 2, which gives me 55. Then the mean value theorem is telling me that there exists a time t in the open interval from 0 to 2 such that f prime of t is equal precisely to the slope of the secant line. So in this case, 55 miles per hour. But then by using that conclusion, this is really telling me that there exists a particular value of t at a particular time where the speed of this particular car is equal to 55 miles per hour. And that particular time happens to be in the interval from 0 to 2. And if I take you back to the question, this is what we needed to show, right? That the car must have had a speed of 55 miles per hour at least once during the 2 hours. So I think that everything is satisfied because we were able to find a t within 0, 2, where the speed of the car is exactly 55 miles per hour. In example 3, we have to determine where the function f of x is increasing and where it is decreasing. Here is a matter of remembering your theorems. If a function is differentiable in an interval ab, I should say open interval ab, and if the derivative is greater than 0, the function is increasing. If the derivative is less than 0, the function is decreasing. So that means that we have to go ahead and find the first derivative. F prime of x is going to be equal to 6x squared minus 18x plus 12. I will go ahead and factor 6 out. That's going to give me 6x squared minus 3x plus 2. And in order to begin investigating the sign of the derivative, I'm going to find the critical points. I will denote that by CP as we have been doing in class as well. So for the critical points, we're going to set f prime of x equal to 0. That means that we're going to have over here 6 times x squared minus 3x plus 2 equal to 0. Then I will just quickly factor this quadratic. That's going to give me x minus 1 and x minus 2. That implies that the critical points are x equals 1 and x equals 2. And these are valid critical points because my function is a beautiful polynomial. A polynomial is continuous and differentiable everywhere. So x equals 1 and x equals 2 are points in the domain of f of x. So they will remain valid critical points. I drew my number line, and if you notice, I positioned the two factors right here on the number line above the line. I position this x minus 1 right here and x minus 2 right here. I also position the critical points on the number line. And I put a heavy dot because these are the points, the type of critical points where the derivative is equal to 0. This line over here is all about analyzing the derivative, not f of x, f prime of x. What we are going to do now is to pick a test point to the left of 1, a test point between 1 and 2, and a test point to the right of 2. And remember what I said in class. I said that intervals between critical points, between two consecutive critical points, the derivative never changes direction. So this is why we can always go ahead and pick one convenient test point. We don't have to choose 2 or 3 or 4, just one. That's enough to determine the sign of the derivative. So then, doing that, if I choose 0, because 0 is to the left of 1, then the x minus 1 factor, if I plug in 0 here, I'm going to get negative result. X minus 2, imagine that I do 0 minus 2, that's going to be negative. A negative times a negative will give me a positive. So this is telling me that f prime of x is bigger than 0. In other words, the function is increasing in that interval. Now, the interval from 1 to 2. Let's say that we choose 1.5 as a test point. If I plug in 1.5 in place of x here, I'm going to have 1.5 minus 1, and that's going to give me a positive number. So positive, positive here, and if I do 1.5 minus 2, I'm going to get a negative value. A positive times a negative is a negative. So this is telling me that f prime of x is less than 0. In other words, the function is decreasing between 1 and 2. And now for the final interval, let's pick 3, something simple. If I plug in 3 in x minus 1, I'm going to get positive, positive, and the same thing over here. So then a positive times a positive number gives me a positive. That means that f prime of x is bigger than 0. In other words, the function is increasing. What I have to do now, as a conclusion, is to write the intervals in, let's say, proper interval notation. So I'm going to say that f is increasing in the interval from negative infinity to 1 and from 2 to positive infinity. And f is decreasing in the interval from 1 to 2. Question 4 is very similar to question 3, only that now I have a different function. But the question is the same. We have to find the intervals where the function is increasing and decreasing. So if you notice, I did exactly the same thing as before. I found the first derivative. Once I do that, I have to try to investigate the critical points. Well, I have to figure out the values of x where the derivative is equal to 0 and the values of x where the derivative is undefined. The derivative is equal to 0 when 4x is equal to 0. That means when x is equal to 0. And this is a valid critical point because if I take 0 and I plug it back in the function is beautifully defined. Now, the other critical points will come when the derivative is undefined. And that happens when the denominator is equal to 0, which is precisely when x is equal to plus or minus 1. So x squared minus 1 is equal to 0 when x is equal to plus or minus 1. And again, if I take plus and minus 1 and I substitute those values in the function is defined. That means that we found 3 valid critical points, 0 and plus and minus 1. You can see here the same setup as before, the number line, and this number line is representing the behavior of the derivative. I now included the numerator and part of the denominator. I didn't bother with 3 because it's just multiplying by positive 3. The sign of the derivative will not be affected by 3. And now I'm going to go ahead and pick a test point in this interval, a test point here, here, and here, and try to figure out what is the sign of f prime. So to the left of negative 1, I'm thinking negative 2. Keep it simple. If I plug in negative 2 right here in 4x, I am going to get negative 8. So then that means negative, negative. And then for the denominator, if I plug in negative 2, I'm going to get positive, positive. A negative times a positive is going to give me negative. So then that means that f prime of x is less than 0. In other words, the function is decreasing in that interval. Now I'm going to go ahead and choose a test point between negative 1 and 0, negative 0.5. If I plug in negative 0.5 in place of x, I am going to get negative, negative, and over here, same thing, negative, negative, so then that means positive. That means that f prime of x is bigger than 0, the function is increasing. In the other interval, I can choose 0.5. So this factor will be positive, the one below is going to be negative, I get a negative result, then that means that f prime of x is less than 0, the function is decreasing. And finally, I can choose 2. So then when I plug that in, positive, 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 f prime of x is bigger than 0, the function is increasing. As my conclusion, I will say that f is increasing in the interval from negative 1 to 0 and 1 to positive infinity. And f is decreasing in the interval from negative infinity to negative 1 and also from 0 to 1. Example 5 is asking us to use the first derivative test to analyze and to sketch the following functions. In class, we did part A, so here I'm going to go ahead and focus on part B only. Just as we did in class, the first thing that we're going to do is to find the first derivative. So then g prime of x is going to be equal to, using chain rule, that's going to be 2 cosine of x times negative sine of x. And then over here, plus cosine of x. It's very important to remember that we're only going to focus on the open interval from 0 to pi. Continuing now, we want to be able to find the critical points. Now, this function is made up of sinusoids. Sinusoids are continuous and differentiable everywhere. So then the same thing is going to happen for g, continuous and differentiable everywhere. So in order to find the critical points are going to come from setting the derivative equal to 0. The derivative will never be undefined. So just set it equal to 0. So g prime of x has to be equal to 0. In other words, we're going to have that 0 is equal to negative 2 sine x times cosine of x plus cosine of x. Okay. Now, practically, what we have to do is to solve this equation. So just using pre-calculus skills. I'm going to go ahead and factor cosine of x out. When I do that, we're going to have negative 2 times sine x plus 1. And then that implies that cosine of x must be equal to 0, or that this factor right here is equal to 0, which means that sine x should equal to 1/2. So all that I have to do now is to solve these two simple trigonometric equations. And here you can put into practice all of the skills that you learned last year when solving trigonometric equations. So from here, from the first one, we get that x is equal to pi over 2. And that's going to be pretty much it, because we need to remember that we're working in a defined interval here. Remember, the interval goes only from 0 to pi. So within this interval right here, only pi over 2 satisfies this condition. Now, for this one over here, we're going to have two possibilities. X is equal to pi over 6, and x is equal to 5 pi over 6. Finding the critical points is crucial here. Remember Fermat's theorem in the previous section. It told us that if a particular y value is a local max or a local min, then that local max or local min happens at a critical point. So then this is why in these problems, whenever you have to find the local max and the local min, you want to investigate what happens at the critical points. You want to find the critical points, because if we're going to have a local max or min, it's pretty much is going to come from there. Now the first derivative test will help us decide which of these critical points will determine a local maximum or a local minimum value. We're going to go ahead, plot them on a number line, and then analyze the sign of the derivative. And remember that what we want is to have the derivative changing signs on either side of a critical point. Now we have the number line where I put the two factors of the derivative, cosine and negative 2 sine x plus 1. That came exactly from this step right here onto here. I also included the critical points, and I put a heavy dot on them indicating that the derivative is equal to 0 there. And I put the endpoints of this open interval, put soft brackets indicating that 0 and pi are not part of the interval. So now I want to investigate the sign of the derivative here, 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 and here. We're going to do that by choosing test points again. So in the first case, right here, cosine is going to be positive. That means that I'm going to have positive, positive, and then negative 2 sine x plus 1 is going to also be positive. And again, I take a value between 0 and pi over 6. For example, you can take pi over 8. And then you substitute pi over 8 here and pi over 8 here. Do a quick computation, and you're going to get the sign of these factors. A positive times a positive will give us a positive here. That means that the function is increasing in that interval. Then we're going to go to the interval from pi over 6 to pi over 2. You can choose, for example, pi over 3. And you can plug pi over 3 into x, and we're going to get plus, plus, and minus, minus. That means that the derivative is going to be negative. Immediately, I know that at pi over 6, I'm going to have a local maximum, because the derivative changed from positive on the left to negative on the right of pi over 6. Now we're going to look at pi over 2. When I pick a test point between pi over 2 and 5 pi over 6, I end up getting negative, negative, and over here, negative, negative. That means a positive derivative. Negative derivative on the left, positive derivative on the right. That is telling me that we're going to have a local minimum at pi over 2. And then continuing with the last interval, we're going to have negative, negative here, positive, positive, negative, negative. So then this is telling me another local maximum at 5 pi over 6. Now, what I did over here to save a little bit of time for the sake of the video, I came and I immediately calculated the y value when x is pi over 6. So f of pi over 6, I took pi over 6 and I substituted that with my calculator into the original function right here. And I got approximately 1.3. Same thing with pi over 2, 5 pi over 6, and with pi. Actually, and even with 0. At 0 and pi, I'm going to have open circles because the interval that I was given was open. It excludes those x values. And then at pi over 6, this is where we have the local maximum. It's a little bit narrow, but you can kind of tell that there's a little bit of a mountain, a little bit of a valley here, and another mountain for that local maximum. Now, if you want to try to investigate what happens with the x-intercepts, then you go back to the original function. You set it equal to 0. I use the Pythagorean identity here. I factor a -1. And then you can, this quadratic here doesn't factor, so then that means that you have to use the quadratic formula. I didn't show that step because what you're going to find when you use the quadratic formula is that the x-intercepts are outside of the interval 0 to pi. They lie in this interval here, in this area right here. So there were no x-intercepts in the interval from 0 to pi. Finally, we have example 6. This is a fun one. We are being told to suppose that f is a function that is continuous for all real numbers. And the graph of the derivative function, f prime, is shown below. So this graph right here, this is the derivative function. What we're going to do is try to answer these questions here. A is asking us for the domain of f prime. That's straightforward. Just look at the graph. If you notice, the domain increases from left to right. This is dotted. The y-axis is dotted. That means that we have a vertical asymptote there. And we can see that by the infinite behavior of the graph on either side of the y-axis. Then we see a jump discontinuity right here. So we know that 2 is not in the domain. Everything else is beautifully continuous. So then to answer the question, part A, the domain of the derivative includes everything from -infinity to 0, union from 0 to 2, not including 0 and 2, and then union from 2 to positive infinity. Now part B. Part B is asking us to list the critical numbers of f, or in other words, the critical points. So remember that this is the derivative. The critical points take place when the derivative is equal to 0 or the derivative is undefined. The derivative is equal to 0 at x equals -2 and at x equals 4. So I know that -2 and 4 are critical points. And the derivative is undefined at x equals 0 because of the vertical asymptote, and also at x equals 2 because of the jump discontinuity. So that means that we have found our critical points. The critical points are going to be the values of x, beginning with -2, 4, +2, and 0. On to C. At what numbers, x, if any, does the graph of f have a horizontal tangent line? To have a horizontal tangent line, that means that the derivative has to be equal to 0. And that happens precisely when x is -2 and when x is equal to 4. D, at what numbers, x, if any, does the graph of f have a vertical tangent line? To have a vertical tangent line means that, for example, f could look like this. Imagine something like that, right? And we're going to assume that it happens at this particular value right here. So you notice how the tangent lines are increasing, 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 getting almost vertical. In this case, same thing over here. And pretty much the tangent line becomes vertical. That means that the slope of the tangent lines are getting extremely, extremely large, to the point where at this particular value of x right here, from both directions, the slope of the tangent lines are going, let's say, to infinity. That leads us with a derivative that tends to go to positive infinity at either side of the value of x. So if I look at this particular graph over here, the infinite discontinuity happens at x equals 0. So then that means that the tangent line happens to be vertical precisely when x is equal to 0. Now E is asking at what numbers x, if any, does the graph of f have a corner? To have a corner, that really means a sharp edge. Let me draw you a possible graph, let's say, where it exhibits a corner. For example, I suspect that the corner happens right here at x equals 2. Look at this. When we approach 2 from the left, the y values are approaching positive 2. So the limit from the left is equal to 2. And the limit of this function, of the derivative, when we approach 2 from the right, is equal to 1. So to the left of 2, the derivative, the slopes of the tangent lines, are approaching 2, and then on the right of 2, the slopes of those tangent lines are approaching 1. A possible graph of the derivative of the function, could look like this particular function right here. And again, this is not perfect. This is just to give you a kind of a visual of what may be happening. Notice how in this particular case, again, I am assuming that this is your f of x function. If I draw little tangent lines, the slopes of those tangent lines are approaching a particular value. I'm assuming that they're approaching 2 from the left. And then if I draw tangent lines over here, they are approaching, for example, 1. And it is precisely here where you may see the sharp corner. So therefore, to answer the question, we are going to say that the possible corner happens at x equals 2. Now in part F, they're asking us on what intervals is the graph of f increasing. Remember that to be increasing, that means that f prime of x has to be greater than 0. So I'm going to look at my graph, and then I notice that on this part right here, from negative 2 to 0, the function f prime, the derivative, is above the x-axis. So f of x is increasing from negative 2 to 0, and then from 0 to 2, because the derivative is positive there. And then in this tiny area right here, from 2 to 4. So we're going to say that f is increasing in the intervals from negative 2 to 0, and then from 0 to 2, and from 2 to 4. And finally, g, He's asking for the intervals where the graph is decreasing, so I look for the derivative being less than 0. And that happens here from negative infinity towards negative 2, and then from 4 to positive infinity. So we will say that f prime of x is less than 0 in the intervals from negative infinity to negative 2 and from 4 to positive infinity. So these are the intervals where the function is decreasing.